Welcome to our workshop on high performance computing. My name is Avendaño-Franco, and on this video we will talk about resource management, Torque and Moab. On a cluster, several people, and sometimes tens, hundreds of people, of individuals, are working concurrently on the system for their research. So, in contrast with your own machine, where you have the control of the machine and you decide what to run and when to run and how to run it, on a cluster, you are supposed to declare your needs and run your simulations, your modeling under very specific conditions. So in such a way that the system can orchestrate the execution of your jobs, but also others people's jobs. So for doing that, clusters usually have what is called a resource manager and a scheduler. There are several of them, and one very popular commercial version of those is Torque and Moab. Torque is just the resource management, so it means that it has some run some programs on the head node and on each individual compute node that monitor the resources available on the cluster and is able to read your resource declaration, and you will see that in a minute in the video demonstration, that are required for your job. So it will keep an eye on what you ask for a job in terms of CPU, number of cores, amount of memory, and amount of time for running the job, and it will look into the resources that are available on the system. The decision on when and how your job will be allocated on which compute node and when that allocation starts is responsibility of a scheduler. So Moab is a commercial scheduler from this company, Adaptive Computing, and they basically integrate the scheduling and also the monitoring of the health of the whole cluster, and also produces some reporting and tools that are very useful for the system administrators of the cluster. So from your point of view, among all the commands related to those tools, you actually just need a few of them. So I made a selection of the 6 commands that you actually need to know, be aware of them, for basically most of your interaction with the cluster, for submitting jobs, for monitoring jobs, and monitoring your queues in case that you have one. There are a couple of commands in the Torque side, and there are a few commands on the Moab side. So we will look into them and we will learn what each command is actually doing for you. So let's go back to the demonstration screen right here. So right now I've downloaded the data from this lesson, so for all these episodes, and I'm located right now on the 05 job. So all the data that I create, I prepare for you for following these tutorials. So let's have a look on what is around here. So I have a few files. In particular, I will be working with one C code. That is this. Here I have this small code. So you see, it's actually a very small code. It's written in C. It's using MPI. So this code is intended to be to work in parallel. Parallelism is something that we will not discuss much on this lesson. But just for you to know that parallelism is something that is not automatic, it's something that you need to program somehow for your application. So your application could or could not be able to parallelize. It depends on how that was developed. And basically this small program, this small example of an MPI program is showing in a small message saying, okay, on this processor and the number of sibling processes that are running with it. So it's a very small example of an MPI execution. So I will be closing this. And if you are running on your own computer, you control how this code will run. For compiling this code, you need to load some modules. We will see this in more detail on the next episode. But right now, what I will be doing is loading the GCC compiler that I need and the MPI library that I need to compile this code. So I will be loading this link GCC, let's say 9.3, and the module for parallel is OpenMPI, and the 3.16 for GCC 9.3. So we will see this in more detail. Right now, this is a little bit like magic. So now I'm able to compile this code. This code compiles like this. This is a wrapper for the C compiler through MPI. Hello, the name of the source code, and I will be directing the output of this, the name of the executable. I will call it hello. So this is how you compile this code. Now, if you see here, I have now one extra file here called hello, and this file is executable. So now, if you own your own computer, you can perfectly run this with the number of processes that you want. And again, I can do this because this program just takes a few seconds, and I can execute this. It will show some message. You can ignore those messages here, and I basically call your attention to these 4 lines. Forget about everything else. So I'm running on creating for processor from process for running on this node, and that's it. It took a few seconds. But now imagine that all the people that is connected to the cluster do exactly the same, and this program doesn't take just a few seconds, but take hours. Of course, the head node is not capable to handle that load, and also the entire cluster is not the head node. The cluster is the head node that is the front door for hundreds. In our case, it's just 110 compute nodes, and you are not using them when you are running this way. So for running a job on the cluster, you are supposed to write a submission script and a text file that will indicate which are the resources that you need for executing your job, and which are the commands that need to be executed one by one to get the job done. So I create one for you here. So we will look into this. So this submission script. So first line, this is called a shebang. This is basically an indication that this is a script. This is a bash script. So this is a perfectly fine script meant to be executed by Linux. These lines here, the next 4 lines here, from here to here, are lines that are ignored by bash, by the shell. But they are very important for Torque. Torque is actually reading these lines and ignoring everything else. is reading each line of those and associating some information from them. So the first line, it will indicate that the name of the job is hello, in uppercase. So each job can have a name, and the name is for you to identify your job from the multiple jobs that you can launch on the cluster. So it's perfectly fine if you end up submitting hundreds of jobs. Some people do. They can handle that volume of execution. So don't feel constrained that you had just run one job at a time. By any means, you can run several of them, many of them if you want, up to a certain limit. Beyond a few hundred, it will be we can have an issue here, but 100 jobs is not that unusual actually. So this line is declared on which queue we are submitting this job. We will see this in a minute. So there are several queues, and you can associate this with the kind of queues that you have in a supermarket. You see, in a supermarket there are normal queues. There are some self-paying queues, that we can think about them like interactive queues. And there are a queue or there are a few lines for people who is just purchasing less than 10 or 15 items, so like a fast queue. So same idea here on the cluster. We can have several queues where you declare how big is your job, for how long you're planning to run it, and according to that there are several queues. And of course, if you are running for 1 week, it's okay for you to wait 1 day for getting the job starting. If there are too many jobs in that queue, you probably need to wait a little bit. But if you are running on 1 day queue, in a queue that is meant to run for 1 day, well, you are probably fine waiting for a couple hours for that job. If you are running on a queue that is just for 4 hours, and that's exactly what I am asking here, I would like to use the standby queue. That is kind of a fast queue. Many people submit jobs there. The jobs are meant to run for 4 hours maximum, and this queue moves very dynamically. So it's a good queue to select in this case. So here I am asking for 2 nodes. For this exercise, I will reduce my expectations because I need this quickly. So I will be executing in just 1 machine, 1 node. So this is what I'm doing here. Number of nodes, just 1. Number of cores, so number of processes per node, 4. So I can actually ask for 8 processes here. And I would like to run for 1 hour. I actually don't need 1 hour for this, so I will even reduce this. This small execution takes actually a few seconds, so I can reduce this and ask, okay, now I just need 10 minutes. You should know for how long your job needs to run. There is no easy way to know that before you submit the job. So what you typically do is that you submit the job on a large queue. You overestimate the amount of time that you need, and you learn from there, and you use that knowledge for the next jobs that you launch that are similar in structure. So if you realize that you need something that is almost 1 day and you never cross that, so you are fine. You don't need to ask for the week queue. You can run on the 1 day queue. And this last line here is something that I often use. This line is basically merging the 2 outputs that you get for a job. On a job, you typically have 2 outputs. One is called the standard output, another is called the standard error. Though they typically go into different files. Very often the standard error ends up being empty. So I don't want to overpopulate my file system with empty files. So I merge those with this command. Next, this now is shell script. So when your job starts running on the compute node that it receives for running your job, you will be located on your home folder, and that is probably not the place where you want to be for executing your job, because you have all your program and your data and all what you need for that execution in a different folder. So this command cd will change the directory, and this variable, that this is an environment variable that is set up for you when the job starts, points to the location where you submit this job. So it's actually the location where you have your files and all your inputs for this. So this is a very good idea to use this on your submission scripts. Some people write explicitly the location or where you want to go, but in that case, this way of working is better, because you don't have to edit this file that much. You can keep this as a template, and you can use it on different execution on different folders. Next, notice that when I compile this code, I need to load some modules, and we will be talking about modules on the next session. So right now, this is a couple of lines that will prepare the environment for me for being able to execute the commands that I need after that. So the first line will purge the environment, so it will create an empty environment for me, and the next line I will be loading exactly the same modules that I use when I compile this code. So the GCC 9.3 and the OpenMPI, the library for parallelization, with this version that I used a few seconds ago for compiling this code. So now here I request a course. So here I should be consistent. I actually don't need this. OpenMPI is able to figure it out that you are executing on a course, but I always like to be explicit on those things. So npm run is a special program that you need when you are running in parallel with MPI, and this is a declaration of the number of processes that you need to create for running this code, and the name of the program that you want to run. Hello. This is my submission script. I will be saving this file. Control X. This is a command on VI for saving and leaving. So let's have a look at this with cat. So this is my submission script. I have one job, and I will be submitting this job. So for submit the job is the next command, and the first command actually that we will be learning here from Torque is this. I'm submitting this job on the cluster with this submission script. When you hit enter, you receive a number. This number is an identifier for your job. Each job on the cluster receive a different number for it, and you can monitor that job, and we will see that. Those are Moab commands. So the next command, it will be on Torque, and is Qstat. And there are several arguments that you can use for Qstat. One is, for example, for showing the jobs that are on associated to my username. So here I have one, and I have this line here, This is my identifier. This is the job name. This is what I request in terms of number of nodes. This is what I request in terms of number of cores. And this is the amount of time. And this letter here indicates that this job was submitted, was executed, and now is complete. So the C stands for complete. So this job finished correctly or incorrectly, but it's complete. And it was because this job is it's a very tiny amount of resources that it found a way of submitting this job quickly. The scheduler Moab found a good node for executing this job, and the job was executed. So I will use another command for showing you the different queues on the system. Is this, and I will have to reduce the size of this. Let me see if I can do this here. So I will be resizing this. Okay, at least like this. Qstat minus Q, uppercase Q. It will show you all the queues on the system. The name of the queues on Thorny are slightly different compared with the names of queue on Spruce. If you receive an account for Spruce, you can execute this command, but you will see a slightly different output. So we always have this standby queue. This is a queue for 4 hours. Notice that many people submit jobs here. We have 3,400 jobs here. We have this number of jobs in queue, this number of jobs in execution, and a number of jobs that are on hold, meaning that they are not running, but they are not accruing priority because they are not running, while those jobs in queue are accruing priority over the time. That's one queue. Another queue that is important for you, this is one queue that some people use is for jobs that requires a lot of execution for a long time, for a week. So we have here 45 jobs. From those, 21 are running right now. This is another queue on the community with community nodes, so queues that you can use freely, that is intended for one day. And this queue is for people who use GPUs. Either you are using molecular dynamics or you are using deep learning or neural networks of any kind, and you can take advantage of GPUs. This is a queue that you could be interested on working on. We have 67 total here, and we have 12 running. This is a queue that is particularly heavy. Many people want to run jobs on this queue, so this queue always is busy. And this other queue in community is for people who requires 1 week of execution and an extreme amount of memory. So one node of those has like 760 gigabytes of RAM. So this queue is for big jobs that take a lot of memory. And there are some other jobs that are owned by researchers. They buy nodes, and they have priority on those nodes, so they can execute if they want to. They can submit jobs to their own queues, and in the worst case scenario, in 4 hours, if the job was running something on standby, it will return back to the owner, and the owner has the ownership of that, or will receive priority on that node for as long as they need to run. So even beyond 1 week. So if for some people a week is not enough, so they basically buy nodes and they can run for an extended amount of time on their own machines. And we have here on a small queue the for debugging is just for 15 minutes. And we have here another queue that is for interactive jobs for with GPUs. Now let me create, okay, so this job finished, but before that I will be editing my submission script again, and I will return into the original version where I have here I have 2 nodes, and here I have 40 cores per node, and here I will have 80 cores total. So I'm taking entirely 2 machines with 40 cores each for running this execution. So I will be leaving this. This probably will take more time for running. Qstat. So I will be executing this, and in the meantime, I can check. I can show you other commands that you can use. So check job. This is a command. This is the first command that we will be learning from Moab. Check job. I usually use it with -v, so to get a more verbose output of this. And the command, let me see. Let me learn first. Okay, what's this one? The number that I have here. So check job. This job that finished a few minutes ago, and I will show me a few things that I could be interested in learning from this job. So I will be entering here with Tmux on copy mode, so I can scroll this back. So this job, it has this identifier, job ID. This is the name of the job. The status of that job is complete. Complete doesn't have any meaning of good or bad, correct or incorrect. It's just that the job is not running anymore. The return code, usually if the return code is 0, means okay, means that the last command that was executed in your submission script was okay, and the return code for that is, in that case, is 0. This was the whole time for that job. So this job ran for 4 seconds actually, out of the 10 minutes that I actually request for it. And this is the time when I submit the job, and this is the time that was in queue. Notice that the job was in queue for 1 second. So basically Moab found a good compute node with 8 cores available for executing my job, and it associate that job immediately to that node and start executing there. So I asked for 8 cores, so you see here that this job is so little that it will not show any metric on cores, and you don't pay attention too much to this. It only actually works when something runs for more than 1 hour or something, or actually several minutes, but that show you the amount of cores that you are actually using. So how well parallelized that code actually is. This is the actual name of the compute node where this job was executing, was rent. And here that's probably it. And here I have the name of the submission script and what was the working directory for this job. So it gives me this command offers me information about this job. Check job, some command, and one command that you should learn from this. Qstat, let me see my job. So Qstat, Franco. Okay, my job is now on the system. Notice this is the job ID that I have for this job. The job I request 2 nodes, a total of 80 cores, and the job is currently in queue. So Moab has not been able to find a couple of nodes entirely empty for me for my job. So one thing that I could be asking is when this job will start running. Some people ask for that. So this command will show you an estimate on when this job will be actually running. So take always this information with a grain of salt. Things could change and you can get a different timing if you execute it again, but this gives you basically an estimate on when this job will start. It's basically saying, okay, this job, it seems that that Moab is able to find a resource for this job in 7 minutes. So it's basically measuring all the jobs and when those jobs will probably end, and according to that it will figure it out if there is any chance of getting a couple of nodes empty, free, entirely free for me to run my job. So it could be shorter if those jobs that are supposed to be running for 4 hours end up running in 3 hours or 2 hours. So the nodes could become free earlier, and I could be running earlier too. And it all comes with the different changes, and this is very dynamic how they change. So if I execute again, my time is going down, so it seems to be working fine. I have 5 minutes probably for getting this job running. So let's go here, and so I show you check job for monitoring all the details, the specifications of the job. Show queue, I use it now. We'll use it now. Show queue. I can see all the jobs running on the cluster. So this is one way of looking into them. All the jobs in different ways. And here I have a vision of all the jobs associated to me. So show queue, the functionality overlaps with Qstat from Torque. It basically shows the jobs and the queues and they are moving, but this is coming from Moab. So this is another command that you should be learning. So when you advance with this, you end up with having multiple jobs, maybe 100 jobs running on the system. So this is one way of monitoring how those jobs are moving. And let me see, I would like to create a new one, and let's edit this one here, and I will create a new job, and I will put the name to this so you come up with what I'm doing. We'll be submitting this job, Qstat, and I got this number, and I realize that the job is in queue, and if the job is actually a heavy job, it will take several minutes for that job to start running. So I could realize, oh, I made a mistake and I need to change something on the script. and this job is a waste of time. I cannot allow this to run. It will serve no purpose on that. So I can cancel this job. So mjobctl is the command for doing that, with this argument minus c.c and the job ID, so 246. You can kill the job. It takes a while. Sometimes if you realize immediately you want to kill the job, you will get an error message, because it takes up to 2 minutes to get the job inside the system, inside the database that is controlling all the execution. So, but after that, the job is registered and you can kill it. So this way you can cancel a job that is in queue or is even running. If the job is running, it will be killed. So show queue. Franco, and it will show that this queue is still waiting. So let's see. I was checking at this. Oh, the time changed for this. So something happened, and now I have a different timing. So now I have to wait 41 minutes for this to run. What eventually happened here is, and I was supposed to run on one, I'm running on standby. So standby is made from community nodes and nodes that belong to owners, to people who bought those nodes for them. So if the job, if the system receives a job from an owner, and I'm supposed to be running on that node will not be associated to me because it will get priority for the owner. So it seems to be the case, and at that moment my job was rescheduled for a different compute node, and now I got a different timing, so I need to wait 41 minutes for getting this job running on the system. So and this comes with a message. So when you create a job here, you should be very careful on associating the right amount of resources for your job. Now, if you ask for too much, more than you actually can take advantage of, not only your job will run slower, so just from asking for more nodes and more codes doesn't necessarily mean that your job will end up quicker. It could actually become slower, and also requesting more resources means that it's harder for the scheduler to find those resources for you, so you will be waiting more on the queue. So always tailor and always find a balance between the amount of resources do you actually need and the amount of resources that you are satisfied asking, in such a way that your job will become running as soon as possible. So right now, asking for this job will take much longer than the amount of time that I was planning for this video. So that's it. Those are the commands that I would like to show you. If you learn those commands, you probably can do most of your stuff of your jobs here. The last command is when you want to run interactively, and for doing that is Qstat -I, and by default the queue is standby. So, and by default is requesting just one core and one node. So executing this will give me immediately one, or immediately not, but relatively quickly, a node, an interactive for interactive execution. So notice that the name of the node where I am currently located, it's not the head node. The head node is this one, and now I on a compute node, and I use this coloring for me to know on which kind of node I'm actually working. And I can execute here. I can run my programs here. I can go into introduction to 05 job, and I can do whatever I want with this. Now at this moment I need to modulo GCC 93 parallel OpenMPI 316 GCC 93, and I can execute this hello. So this version of MPI, OpenMPI, communicates with Moab and figure out the number of cores that I request for my job. By default is 1. So notice that there is just one line here on this. If I execute this more explicitly, requesting for 4, I get an error because with this OpenMPI, I just request one core. So I will be just running on 1, but I was requesting an execution with 4. And so this is an interactive execution, and you can use it, but this is not the main purpose of a cluster. Remember that this could be handy when you are preparing and you are exploring a few things, and you would like to control the details and you would like to go manually and execute a few things. But the purpose of a cluster is running non-interactive jobs. That's the most efficient way of running a cluster. So try always to submit jobs instead of running interactively. Beginners has a tendency to always work on interactively, so I invite you to overcome that tendency and start writing your submission scripts and work with them. So with this, I will be finishing this video. I hope that I'll cover the essentials of submitting jobs on the cluster, and we will see you on our next video. Thank you very much. See you next time. Bye.